in the example before this, it was purely just looking at an exploration of a fourth degree polynomial that is used to approximate a function. And the pattern that emerged that we saw was that if I was looking at a fourth degree polynomial, in this case, the fourth degree corresponded with needing what the fourth derivative was evaluated at 0. So here, the fourth derivative at 0 was 5, so that showed up here, over 4 factorial to the fourth power. This happens to be the third derivative at 0, the second derivative, the first, and notice that as you go down, so does the exponent in it. That corresponds with the factorials at the bottom. And so what emerges is that the Taylor series is a way that we can come up with any function, a series that approximates any function centered about whatever value we want it to be centered about. So let's talk a little bit about what this centering means. When we first discussed on the other page an approximation for y equals sine of x, we saw that the best approximation was initially at 0 at least, y equals x. And if we think about what y equals sine of x is at x equals 0, the bar with the x equals 0 simply means plug it in. We get a value of 0. If we think about the polynomial approximation that we initially had, y equals x, if we plug x equals 0 in, it was an exact value, an exact match to the actual. And so we say it's an excellent measurement of the actual function when it's about close to the center. So here we see that it's good, excellent around the center, but as you move further away, the error between the actual and the approximation grows. So below here, when we're reading a problem, it's going to tell us where to center it about. And the neat thing with Taylor series is we find that we can find a series approximation for any function, and also to shift that function anywhere we like so that the center moves along with our series so that it becomes a great approximation wherever we want it to be and not just at the origin. So as a reminder to you, when we looked at ln of 1 plus x, that function before, we actually came up with what the series approximation was for that using a template series. We had our series expansion for 1 over 1 minus x. We then changed that to 1 over 1 plus x by changing the input to negative x, and then went on to integrate that to get ln of 1 plus x. And so if you are able to come up with the series expansion for a function using your template series that you've memorized, that's going to be the way you want to go about doing these problems, because that's going to be much faster than what I'm about to show you. When I'm about to show you, think of it kind of as the long, fail-proof way you'll always get the series that you want. However, it does take what they call successive derivatives here to come up with the value of the series that you want. So in this case, the problem above that, again, was strictly just exploratory, but they gave us the value of the derivatives at the center. Whereas down below here, when they want me to construct a fourth degree polynomial, I'm going to need all, the function evaluated at 0 all the way up to the fourth derivative. If I want to come up with a series that matches ln of 1 plus x. And when I see at x equals 0, that's going to tell me this is where the center is at. This is where they want me to center my series. So let's go about what the steps are. So all it is first finding the values of the successive derivatives. So let's start off with f of x. So write your function out first, ln of 1 plus x. Feel free to pause if you need to, if I'm going through the derivatives too quickly, but you're just simply taking successive derivatives all the way up to the fourth derivative. So here we've got negative 1 over 1 plus x quantity squared. The third derivative would be equal to, and if you need to, rewrite this as negative 1 plus x to the negative 2 power. Remember, multiply the exponent and then deduct by 1. We get 2 over 1 plus x cubed. And our last derivative is going to be negative 6 1 plus x to the 4th power. For each one of these function values, what we're going to do is evaluate it at the center. So what I'm going to do is draw a bar and say x equals 0 beside each one of these. This is just to say evaluate at x equals 0, plug x equals 0 in. Those are the values that were given to us above that we're now going to find. So if I plug 0 in for ln of 1 plus x, ln of 1 is equal to 0. So switch colors here. So this is equal to 0. Plug it in, and you guys get that this is equal to 1. If you plug x equals 0 into the second derivative, you guys get a negative 1. If you plug x equals 0 into the next one, we get 2. And then the last one, we get negative 6. Now these green values are the values that I'm going to transfer over, and let me go ahead and write the pattern that we saw above there. We saw that we needed the 4th derivative evaluated at 0, the center, over 4 factorial x to the 4th, plus the 3rd derivative evaluated at 0 over 3 factorial x cubed, and then basically you're going to deduct 1 from each one of these, the 2nd derivative over 2 factorial x squared, plus the 1st derivative over 1 factorial x to the 1st, and lastly, if we still continue that pattern, the original function at 0 over 0 factorial x to the 0 power, which I'll squeeze in down here, x to the 0, which is really just 1. Now if we plug everything in, let's keep the green. I know I kept all of that formula in green, but I'm going to apply the green and plug in these values into all of the derivatives that you guys see here. Okay, so if I go ahead and do that, I get the 4th derivative at 0 was negative 6 over 4 factorial x to the 4th, plus the 3rd derivative, which is 2 over 3 factorial plus, and I'll keep the color the same, we're going to need the 2nd derivative over x squared plus the 1st derivative over 1 factorial plus the original function over 0 factorial, which is 1, x to the 0 power, which is just 0. And in green, I'm going to put all of the derivative values that I got. So the 2nd derivative was negative 1. The 1st derivative was 1. And then the last function value evaluated at 0 is 0. So that's my constant. And so if I were to simplify all of that, which if this was a free response, you can leave all your factorials unsimplified. You can just leave your answer as such. But if it was a multiple choice answer and the function values were reduced, you might go on to see the answer written in different orders, and you might see the function values reduced as well, like 4 factorial expanded out and reduced from there. So for now, we'll keep it as such. And then this is the polynomial that is the 4th degree polynomial that approximates ln of 1 plus x around the center x equals 0. And as we shift the center, we'll see that we'll also have to change the values that we plug in here. It's always the center evaluated.